Welcome to this first video in the playlist on field theory. In this video, what we're going to talk about is the characteristic of a field. Now, before we actually turn on to that topic, let me just say that this playlist on field theory, it's intended to follow the playlist on ring theory, which itself was intended to follow the playlist on vector spaces, which itself was intended to follow the playlist on group theory. So this is my fourth playlist on abstract algebra. Okay, so the viewer is assumed to have a lot of knowledge of abstract algebra already before starting this playlist. Okay, so that's just a little bit of an introduction. Now let's actually turn to the topic of this video. So what we want to discuss is what is meant by the characteristic of a field. Okay, and then we want to prove an important theorem about the characteristic of a field, namely that the characteristic of a field is always either 0 or a prime number. Okay, right. So firstly, let's just do the setup. So we're going to be working with a field. Okay, so we'll denote our field capital F, and I'll just remind you that a field is a non-zero commutative ring. Okay, so it's a commutative ring that is not the zero ring. You do not count the zero ring as a field. Okay, and it also has to obey the additional important property that all non-additive identity elements, so all elements apart from the additive identity in it, have to have a multiplicative inverse. So a field is a non-zero commutative ring in which all non-zero elements have a multiplicative inverse. Okay, right, so that's just a reminder of the definition of a field. Now let's actually have a look at the definition of the characteristic of a field. So the characteristic of a field is a number that is associated with all fields, and it's a non-negative integer, so it can be 0 or it can be a positive integer, a natural number. Okay? Now, how do we actually define then the characteristic of a field? Well, the way that you work out what the characteristic of a field is you take the multiplicative identity in your field. Okay, so all fields will have a multiplicative identity because they're all non-zero commutative rings. And the other thing to say that's important is that because we know that our field is not the zero ring, then the multiplicative identity 1, which is normally denoted 1, is a separate element from the additive identity, which is usually denoted 0. So we know that the multiplicative identity in a field is not the same as the additive identity. Okay, that's the non-zero portion of the definition of a field. Okay, right. So you take the multiplicative identity in your field, and what you have to ask to work out the characteristic of the field is what is the smallest number of times I have to add 1 to itself to get back 0. Okay, so what you do is you use this element 1 and you ask, okay, what is 1 plus 1? Okay, and you do this in your field, so your field will have an addition law defined on it. Okay, so you add 1 to itself and you get some answer and you ask, is this 0? Okay, if it is, brilliant, you say the characteristic of that field was 2 because I had to add 2 1s together to get 0 back again. Okay, and that's the definition of the characteristic of a field. If 1 plus 1 is not equal to 0, then you continue on, and you say, okay, I'll take the answer to this and add on another 1. So you do 1 plus 1 plus 1. Okay, and again you ask, what is the answer to this in your field? And if the answer is 0, then you say, okay, I'm finished. I ask, how many 1s did I have to add together to get back 0? I had to add 3 together, so my characteristic of the field would be 3. Okay, if 1 plus 1 plus 1 was not equal to 0, then you're not done yet, you would have to continue on. Okay, and you go on and on, adding 1s together until you get back 0. Okay? So, what you ask then, in order to work out the characteristic of a field, is you ask how many times do I have to add 1 together, the multiplicative identity in my field, to get back 0. And it's the smallest number of times you can add 1 together to get 0 back again. Okay, so the number of times that you've added 1 together here to get 0, this will be the characteristic of the field. And I'll repeat again that it's the first time that 1 plus 1 plus 1 plus 1 gives you 0 back again. Okay, so you want the smallest number of ones that you have to add together to get 0 back again. That is the definition of the characteristic of a field. Okay, now, so there is one little caveat to this, of course. What if you can add 1 to itself as many times as you like and never get 0 back again? Okay, so for instance, if you take the rational numbers, which is certainly a field, you can add 1 to itself as many times as you like, and you will just get a bigger and bigger rational, but you will never come back to 0. So you might expect the characteristic of such a field to be infinity, to be defined to be infinity, but it isn't. The way we define the characteristic of a field, where you can add 1 to itself arbitrarily many times and never get 0 back again, is we define it to be 0. Okay, so the characteristic of the rational numbers is actually just defined to be 0, so that's the definition. We are, after all, coming up with the definition of the characteristic of a field. Okay, so we can make it whatever we like. So if it's the case that never does 1 plus 1 plus 1 a certain number of times, a finite number of times, ever give you 0 back again, then you define the characteristic of such a field to be 0. So that means that the characteristic of all fields is either going to be some natural number, that's the case where it actually does come back to 0 if you add 1 to itself a certain number of times, or it's going to be 0, so it's a non-negative integer. Okay, right, so there's the definition of the characteristic of a field. Let's just do another example. So we've done the example of the rational numbers, so I might just write that down. The characteristic of the rational numbers here is equal to 0, and we will do some more examples later on, but let's just do an example right away to get some intuition. I would like to do an example where it does actually end, where you do actually have a characteristic that is not 0, okay, so where you do add 1 to itself a certain finite number of times and get 0 back again. Okay, so let's do the simplest example we can possibly do, working with the smallest field we can, which is the field f2, the prime field f2. Now I'll remind you that the prime field of f2 just contains two elements, 0 and 1, okay, and the addition law on this, I'll just write it out in full. Here's our addition composition table, and I'll just add a little bit of colour on here, so we'll colour it in green here. So now let's draw out our addition composition table. So we'll need a row corresponding to both 0 and 1, a column corresponding to both 0 and 1. Okay, 0 is the additive identity, so it'll add to everything to give the other thing back again. So 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, and then 1 plus 1, okay, that's going to have to be 0, because of course this needs to be a group composition table, and since it's a group, we need all of the rows and the columns in this composition table to contain every element of the set that is the basis for the algebraic structure to be contained once and only once. Okay, so you cannot have 1 there, otherwise you'd have 1 appearing twice in this row and also in this column here, and 0 not appearing at all. Okay, so 0 has to be there, and then drawing out the multiplication composition table, and I think I'll add a bit more colour on here, so we'll have multiplication in red here. Okay, again we'll give 0 and 1 a row and 0 and 1 a column each. Now 0 will multiply with everything to give 0, as it always has to if we're working with a ring, and a field is certainly a ring, and then 1 will multiply by itself just to give 1, because after all it's the multiplicative identity. Okay, right, so let's now ask, what is the characteristic then of this prime field f2? Well, of course, this is very simple. If we take 1 and add it to 1 in this field, okay, so according to this addition law, so we ask, what is 1 plus 1? The answer is 0. Okay, so we add 1 to itself once, and we get 0 back again. So that now means that the characteristic of this field, the characteristic of the prime field f2, is going to equal 2, because I had to add 2 1s together in order to actually get back to 0. Okay, so that's the characteristic of f2. So there's an example of where the characteristic is non-zero. Okay, right, and the characteristic will evidently never ever be 1, okay, because the only ring in which it would be true that if you just take 1 1 and get 0 would be the 0 ring, and the 0 ring is not a field. Okay, so the characteristic of a field is never going to equal 1. Okay, so now what I want to do is introduce you to a little bit more notation that's going to be helpful for us when we're trying to prove a little theorem that's going to be useful concerning the characteristic of a field. Okay, so a bit of notation then. So the way that people often describe this 1 plus 1 plus 1 a certain number of times is for a dot notation. Okay, so we often write n dot 1, where n here is going to be some natural number, so some positive integer, okay, a positive whole number, and 1 here is of course our multiplicative identity from the field. Okay, and what this will then mean is 1 plus 1 plus 1 n times. You're adding together n lots of 1. Okay, and the addition is all in the field, so from now on I think I will denote addition in the field by vivid purple. Okay, so these additions here are all in the field. Okay, so n dot 1 means an element in the field. Okay, this is an element in our field, capital F here, our general field, where you've just taken the multiplicative identity of the field and added it together n times. Okay, and that makes sense because n is just a natural number, it's a counting number, so we're just using it here to count the number of ones that we are adding together in the more general algebraic structure, this field here. Okay, so we're using the fact that the natural numbers is the algebraic structure that represents counting here. Okay, right, so there's a little bit of notation, and this has some nice consequences. Okay, so there are two nice properties that this notation has. The first is that if we consider what is n dot 1, okay, plus in the field m dot 1, okay, and let me just colour this in here. So this is addition in the field, so we're taking an element of the field. Remember, this is just an element of the field. It just means this: add 1 in the field to itself n times, so you'll get some answer that's in the field. So this is just an element of the field, and this is just an element of the field. Okay, so I'll underline them both in purple because they're both elements of the field, and we're denoting things to do with the field in purple. Okay, so you're adding those two elements of the field together in the field. Now, this is going to actually equal n plus m, where you add these two natural numbers together according to the way that you would add two natural numbers together in the algebraic structure of the natural numbers. Or you can think of this, if you like, as a subset of the integers, so the way that you would add them together in that group of integers under addition. And then, of course, you'll have dot 1. Okay, now I hope that should be fairly intuitive here, okay, because this just means 1 plus 1 plus 1 n times, and I'll write this out, so it'll mean 1 plus 1 plus all the way up to another 1, and you'll have n lots of them here, and all of these additions, of course, so this addition here, all the way up to this addition here, those are all additions in the field, and then you've got another big plus here, which is that one in the middle, and now you're adding on m dot 1, which is 1 plus 1 plus all the way up to another 1 here, and now you've added 1 to itself m times here. Okay, so now how many 1s have you overall got there? Well, of course, you've got m plus m lots of 1 now. Okay, so you add these two natural numbers together to get some other natural number, and that's how many 1s you've now got. Okay, so this is really just counting. Okay, so that's one of the nice things about this notation, that it works very nicely when we want to consider what n dot 1 plus m dot 1 in the field is going to be. Okay, the other really nice thing about this notation comes from when we consider what n dot 1 multiplied in the field with m dot 1 is going to be. So now let's consider n dot 1 multiplied with m dot 1. Okay, where this is multiplication again in the field, so I'll colour it in there in purple because it's to do with the field. Okay, so again, n dot 1 and m dot 1 are just elements of the field, so of course you can multiply them together in the field. Okay, so what is this going to equal? Well, you might be able to guess this. It's going to equal n times m, where again this now means multiplication in the natural numbers, or if you prefer, this subset of the integers, okay, which we're very familiar with, and then dot 1. Okay, so let's just understand why that's going to be true. Well, it just comes very naturally by actually writing these out as what they actually are. So n dot 1 is just going to be 1 added to 1 added to all the way up to another 1, and that's going to be n 1s overall. Okay, so I'll colour these pluses in purple because again you're adding all of these 1s together in the field here. Okay, so you've got n 1s overall there, and now you are multiplying that, so I'll put a multiplication symbol there. You're multiplying it in the field with m dot 1, which is just going to be 1 plus all the way up to another 1 here, and you've got m lots of 1 there. Okay, so again I'll colour these additions here in purple because they are in the field, capital F. Okay, right, so now how are we going to do that? Well, you'll notice that all of the operations here that we've got, addition and multiplication, they are all in the field, capital F, and of course a field is a non-zero commutative ring, so multiplication distributes over addition. Okay, so we can now just apply distributivity here, okay, and expand it out, and we'll just get loads of 1 times 1s. Okay, and 1 times 1 in any field is just going to be 1, because 1's the multiplicative identity. Okay, so we just need to work out how many 1s are we overall got at the end of that. Well, how many are we going to get? Well, this one here, so if we now just do this bit by bit, so let's consider this one here, okay, it will end up multiplying with every single one of the ones that we've got here, okay, and you'll get 1s being added together for every single one of those multiplications. So how many will you overall get from this one? You'll get m 1s from that one, so this one will end up having m 1s being added together in the overall answer to this just for it. Okay, so we'll get 1 plus 1 plus all the way up to another 1, and we'll have m lots of those just for this one. So I'll colour this in fact I'll box it here in orange. Now of course this is still addition in the field, so I'll colour it in purple there, and I'll just move this up a little bit. Right, like so. Okay, so that I will also just underline in green there. So that's all of the things that come just from multiplying this one with all of the 1s from this bracket here. Okay, now let's do our next one. So we'll do this one here as well. This one will multiply with all of the 1s over here, and we'll end up with another m lots of 1s. So we'll add on to this another m lots of 1s. So we'll get 1 plus all the way up to another 1, and we'll have m lots of that again. Okay, so this is a natural number, so I'll underline it in green. All of these additions are in the field, so I'll colour them in purple. And this is everything corresponding to the red boxed one there. Okay, and then of course you'll do this for all n 1s here. Okay, so you'll have n lots of these m lots of 1 all added together. So this will go on, and you'll have n of these boxes basically. So how many 1s are you overall going to have in this great big string? Well, you're going to end up with n times m lots of 1 being added together. Hence why the answer is n times m in the natural numbers dot 1. Okay, right. So there is another nice fact that comes from using this notation. Okay, right. So now the important theorem. So the important theorem then is that the characteristic of a field can only take on certain numbers. Okay, it can either be equal to 0 or it can be a prime number. Okay, so one of the prime natural numbers, so for instance 2, 3, the numbers that you call prime numbers when you were back in school. Okay, so 2, 3, 5, 7, 11, 13, 17, all of these. Okay, so the characteristic of a field can only be 0 or one of these prime numbers, like so. Okay, so how can we prove that the characteristic of a field can only be 0 or a prime number? So of course it will be 0 if, like the rational numbers, you add 1 to itself as many times as you like and you never get 0 back again. Okay, so that's nice and easy to understand. Now why, if it's going to actually be a natural number, does it have to be a prime natural number? Okay, well, let's imagine that it could be a number which wasn't a prime number. Okay, so let's imagine that the characteristic of a field, which we'll call little n for short. Okay, so this is our characteristic of a field. Let's imagine that it wasn't a prime number. That would mean little n could be written as a times b, where a and b are not equal to 1. Neither of these is equal to 1. Remember, the important thing about a prime number is that it can really only be written as 1 times itself, okay, if you're trying to get the two numbers to be natural numbers. Of course, in the integers it could also be written as -1 times the negative of itself, but we'll ignore that. If we're working in the natural numbers, one of these natural number prime numbers can only be written as 1 times itself. That's the only product that will actually make it. If it's not a prime number, however, it will be writable as a times b, where neither of these is equal to 1. Okay, now why is that a problem? Well, the problem comes from if you consider n dot 1. If n is the characteristic of our field, then n dot 1 is equal to 0. Okay, and importantly, n is the smallest number of 1s that you can add together to give 0. Okay, that's the definition of the characteristic of a field. But now we can use what we've just developed here. We can stick in for n a times b, okay, so this is equivalent to writing a times b, where these two are being multiplied in the natural numbers here, so I'll put a multiplication symbol in there, okay, dot 1 is equal to 0. But now we can use this fact in the opposite direction, okay, we can split this up into a dot 1 times b dot 1 is equal to 0, and now this is true in the field, so this multiplication is done in the field here. Okay, well, it was always in the field, the equation was always in the field, but now the multiplication is in the field. Okay, and why is that a problem? Well, we're working in a field. Now, field is certainly an integral domain. You cannot multiply two elements together in the field and expect to get 0 unless one or both of them are equal to 0. Here we have two elements of the field, a dot 1 and b dot 1, multiplying together to give 0. That implies that one of these is equal to 0. Okay, so let's say arbitrarily that it's a dot 1. So this would have to equal 0, but a is going to be a smaller number, okay, because of course when you product two natural numbers together you always end up with a bigger natural number, well, greater than or equal to a natural number than each of the things that you multiply together, okay. So what that is going to mean then is that because we assumed that this was a proper product, so neither of them was equal to 1, each of these things that we had here had to be less than n. So this is a familiar property from the natural numbers, that when you multiply two numbers together, you always end up getting something that's greater than or equal to the two things that you started off with. Because we know that this is a proper product, okay, it's not 1 times n that we've got here. These are two non-1 elements here, okay, we know that this is a strict less than here. Okay, so a and b have to strictly be less than n. Okay, I hope that's intuitive from your understanding of primary school maths. Okay, so what I can now say then is that I have found you some smaller natural number such that if you add 1 together that with itself that many times in the field, you get 0. That contradicts n being the characteristic of the field, okay, because the characteristic of the field is the smallest natural number, such that if you add 1 to itself that number of times in the field, you get 0. It's the first time you get 0, basically, okay, but here is that contradiction. If n was not a prime number, this would be a perfectly valid argument. I could write n as a times b, where both a and b are strictly less than n. Okay, and then of course it's a times b dot 1 is equal to 0, but then I could split this into a dot 1, 1 added to itself a times in the field, b dot 1, 1 added to itself b times, okay, and that would be perfectly valid. But now, because the field is an integral domain, one of these two things that I'm multiplying together, okay, has to be equal to 0, and that would imply that we have a contradiction of n here, this natural number n being the actual characteristic of the field, because we've now found a smaller natural number such that if you add 1 to itself that number of times in the field, you'll get 0. Okay, so that then is why the characteristic of a field must be a prime number if it's not 0. So the characteristic of a field can only be 0 or a prime natural number. Okay, right, so to end this video then, let's just do some examples. Okay, and we'll do all of our favourite fields, all of the fields that we've actually seen so far. Okay, so we'll do the prime fields and then the rationals, the reals and the complex numbers. Those are not the only fields that exist, there are loads more, and this playlist on field theory is going to be all about exploring those other fields, but so far in the other playlists on abstract algebra we have only met these prime fields and then the 3 classical fields. Okay, so we'll just do those. So let's start with the characteristic then of the prime field. So an arbitrary prime field fp, where this p here is a prime. Well, I claim that this is equal to just that prime here. Just like when we did the characteristic of f2, we ended up with the characteristic of that being 2. Okay, so more generally, the characteristic of the prime field f subscript p, where p is a prime natural number, is just going to be that prime natural number. Okay, so why can I say that? Well, let me just remind you of what fp is going to contain. So remember, fp is just the quotient ring of the ring of integers by the maximal ideal pz. Okay, the principal ideal generated by p, all integer multiples of that prime p. Now, because that is a maximal ideal, when you perform this quotient ring operation, you actually end up with a field here. Okay, now the elements then of this will be the cosets, and we usually denote the cosets by the elements, the representatives that are between 0 and p. Okay, so we usually denote them 0 bar, 1 bar. You don't have to put the bars. For instance, when I was doing F2, I didn't put the bars. Okay, I could have put 0 bar here, the coset that contains 0, and 1 bar, the coset that contains 1, but I didn't bother. Okay, we will put the cosets more generally down here. So we've got 0 bar, 1 bar, 2 bar, and then you'll go all the way up to p minus 1 bar here. Okay, so those are the p cosets that you partition the ring of integers into, and then the way that you define addition and multiplication of these cosets is just the normal way that you define addition and multiplication on the cosets in a quotient ring. You just take representatives from the cosets, add them together, or multiply them together using the operations in the initial ring, in this case the ring of integers, and then you get some answer in the ring of integers, and you just take the coset that contains that. Okay, now let's just consider our multiplicative identity here, which is 1 bar. Okay, well, if we add 1 bar to itself, okay, so if we consider adding 1 bar to itself, when we add 1 bar to itself once, what are we going to get? Well, we take a representative from here, we might as well take the most sensible representatives. Okay, so this is addition in our field here. We'll take the representative 1 from here, the representative 1 from here, add them together in the integers, we'll get 2. Okay, we take the coset that contains that, so that's just 2 bar. And more generally, you can add 1 bar to itself a certain number of times and you'll just go up here. So if you add 1 bar plus 1 bar plus 1 bar, you'll get 3 bar, etc. Okay, so now if we consider adding 1 bar to itself p times, so if we consider p dot 1 bar, and this is why this notation is nice and useful. Okay, so this means adding 1 bar to itself p times. Okay, we'll take a representative from these cosets, we'll take 1, and we'll just add that to itself p times. Okay, so we'll end up with p in the ring of integers, and then we'll have to ask which coset contains p. Well, of course, the coset that contains p is the same as the coset that contains 0, because p is going to be in our ideal here, the principal ideal generated by p. So p is certainly in its own principal ideal. Okay, so indeed, the characteristic of these fields, the smallest number of times that you can add the multiplicative identity to itself to get back the additive identity, is going to be this prime p that's already so ingrained in the structure of this field. Okay, so the characteristic of a prime field then is just that prime that's associated with it. Now let's do our classical ones. We've already done the rationals. Now let's consider the real numbers. Now this is very easy. Okay, if you take 1 and add it to itself a certain finite number of times, again you just get bigger and bigger and bigger and bigger in the real numbers. Okay, there is no finite number of times that you can add 1 to itself and expect to get 0 back again in the real numbers. Okay, so the characteristic of the real numbers is just going to equal 0, and then of course the complex numbers is just even bigger than the real numbers. It's a bigger version of the real numbers. Okay, if you add 1 to itself a certain finite number of times in the complex numbers, you are never ever, I assure you, going to get 0 back again. So again, the characteristic of the complex numbers will equal 0. So the characteristic of all the classical number systems, the rational numbers, the real numbers, and the complex numbers, is 0. Okay, the characteristic of our other toy fields here, the prime fields, is just the prime that's associated with them. Again, those are the only fields that we have met and are comfortable with at the moment. Okay, so those are the only ones we'll comment on in this video. Okay, so we'll end this discussion then of the characteristic of a field here.